Hello, it is my pleasure to welcome you to this workshop, in which I will introduce a methodology for analyzing the effect of fuel composition on the combustion and emission of an engine using the Ricardo software suite. The tools I will be presenting today are available in our 2022.1 and later releases. Without further ado, let me introduce myself. My name is Charles Turquand, and I'm an Assistant Product Manager at Ricardo Software, working with our 3D CFD toolchain, VECTIS. I am mainly responsible for the application areas covering combustion, and in particular, internal combustion engine. I have been with Ricardo for 3 years now, first as a senior software developer in the VECTIS team, with a focus on our combustion model development, and now as an Assistant Product Manager. In the past, I have also worked as the lead CFD engineer in a small CFD consultancy company. I will start this workshop by explaining the importance of a fast and accurate workflow capable of capturing the effects of fuel composition onto the emission and power profiles of a power plant. I will also show that Ricardo 3D CFD Suite is the perfect toolchain to address this complex engineering problem. I will then highlight the various steps involved in applying this e-fuel workflow with our tools. A brief introduction to the engine used in this workshop will be provided before introducing the data inputs and the modeling of the gasoline composition. The setup of a detailed kinetic simulation from scratch will then be presented, and at the end of the workshop, we will answer your questions about this novel workflow. If you are watching this recording offline, please email your questions to rs_support@ricardo.com. New regulations being introduced are imposing increasingly stringent requirements for powertrain emissions. We have the pollutant formation per vehicles already regulated with certification bins for carbon dioxide, NOx, particulate matter, etc. But we also see the introduction of fleet average emissions and the regulation of new species such as formaldehyde and ammonia, both being products of incomplete combustion. The transition to net zero transportation involves the use of synthetic, bio, or e-fuels, all of which can potentially have large compositional variation compared to a baseline, and this may affect quite substantially the power and emission profiles of a powertrain. Thus, there is a need for a predictive toolchain able to simulate the complex phenomena involved in powertrain emissions. This highlights the increasing role of CFD in new combustion system development to reduce both cost and time to market. It also highlights its role as an essential enabler of the virtual product development process. An e-fuel analysis workflow faces 4 challenges. It needs to correctly reflect the fuel composition, and it also needs to accurately measure the performance and emission of the powertrain resulting from this fuel composition. This must be done in both a feasible computational time and with a user-friendly process. This workflow aims at answering to 2 engineering complex problems. The first one being, how does an engine react to fuel modification? While the second is, how can we then modify the fuel composition to match the required performances? VECTIS 3D CFD toolchain is a market-leader detailed CFD toolchain used on a wide variety of applications such as propulsion and thermal management. It includes Ricardo's expertise on powertrain design and is built around the unstructured finite volume solver vSolve, a solver which features key capabilities for IC application such as accurate performance and emission analysis, combustion models and combustion modeling frameworks that are both regime and fuel composition agnostics, but it also supports all types of meshes and motion thanks to its arbitrary dynamic mesh cut cell method. In VECTIS, or vSolve, there are 3 combustion frameworks available, with by increasing order of cost, complexity, and accuracy, the Ricardo 3-zone flamelet that relies on a reduced tabulated chemistry and a level set method for the flame front propagation. A bit more complex and accurate, we have the combustion progress variable, or CPV framework, in which detailed tabulated kinetics is used, and a similar accurate level set method as the RTZA framework. And if we take an additional step towards accuracy, complexity, and cost, we have the Ricardo Direct Detailed Kinetics, or R2DK framework, which uses on-the-fly detailed kinetics and which is capable of very accurately modeling emissions by simulating the various chemical pathways that lead to the pollutant formations. The e-fuel composition analysis workflow works as follows. We start with a reference fuel, a 1D model, so like a wave model of the power plant, which will feed into boundary condition for CPV precursor simulation that will be usually running for 1 or 2 cycles until a cycle-to-cycle converged solution is obtained. The cycle-to-cycle converged solution is then used to provide the initial field for the more costly R2DK simulation, which can then analyze either the multi-component mixing or, after calibration, the combustion and emissions of the fuel formulation. Using this knowledge of both the mixing and the combustion, the fuel formulation can then be modified to improve the emissions. This cycle can be repeated for as many compositions as needed or as many compositions as wanted. In this workshop, I am going to demonstrate the setup using a gasoline direct injection spark-ignited engine that you can see here on the right. This engine features a compression ratio of 10.2 with a bore of 84 mm and a displacement of 0.5 liter per cylinder. The operating point that we're going to analyze is part of an injection timing swing at 2000 rpm and corresponds to the KP6 operating point of the table. Note that this case can be found within a Ricardo software installation in the VECTIS tutorial section. The necessary inputs for this simulation are the geometry, with a pre-processed geometry that is painted, and with the moving boundary motion files, usually extracted from a wave or 1D simulation. We then need the spray parameters in terms of injected mass, rate of injection, particle size distribution, etc. The fuel composition and properties must be known for both the liquid and gaseous phases. Combustion input must also be provided in the form of a chemical mechanism capable of simulating the kinetics of the currently used surrogate. Various timings are required for the spark, start of injection, valves opening, closing, etc. Then boundary condition must be supplied for both the temperature, for the walls, and in terms of mass flow or pressure at the open boundaries. And finally, as mentioned earlier, we need a CPV cloud file, such as illustrated here on the right, which will provide the initial field for the detailed kinetic simulation. Fuel composition can be extremely complex. In particular, gasoline is often composed of tens of species, ranging from short to long hydrocarbon chains, including potentially cyclic hydrocarbon or even sulfur-containing compounds. Accounting for this complexity, even with detailed kinetic simulation, is almost impossible. Some sort of simplification or modeling is required. Usually, this takes the form of the definition of surrogates, which are essentially mixtures composed of a few selected species that are able to mimic the main characteristic of the real fuel. In the case of gasoline, 3 common surrogates are usually considered, the first one being the primary reference fuel, the second is the toluene reference fuel, and the third one is the ethanol enriched toluene reference fuel. These surrogates contain isooctane and n-heptane for the primary reference fuel, n-heptane, isooctane, and toluene for the toluene reference fuel, and an addition of ethanol for the eTRF. This mixture allows to match a few parameters, as I said earlier, such as the research octane number for the PRF mixture, the research octane number and aromatic content for the TRF, and the ethanol fraction, aromatic content, and octane number for the eTRF. In theory, any surrogate can be created. However, some limitations are present. In particular, the liquid component properties must be available, either from the Ricardo installation directory or from the literature, or they must be created. And more importantly, a chemical mechanism capable of accounting for all the species present in the surrogate mixture must be provided. In this workshop, I will be considering 2 commercial gasoline fuels. The first one is a 95 octane rated, and the second one is a 98 octane rated with 20% ethanol. Both fuels are modeled with a TRF or ETRF surrogate mixture, where the first one has 35% aromatics to match the real gasoline LHV, and the second fuel, fuel B, has 23.7% aromatics and 20% of ethanol. The chemical mechanism used is taken from Hiroshima University, called SIP mechanism, and is shipped in multiple flavors for PRF and TRF mixtures with or without ethanol. Additionally, in all cases, it's possible to account or not for NOx chemistry. This mechanism has been selected thanks to its very compact formulation. It's about 98 species for this complex surrogate, and a very good accuracy of a wide range of conditions, both for the laminar flame speed propagation and auto-ignition delay time. Finally, to fully benefit from the state-of-the-art multi-component spray and Wolfing modeling of VECTIS and the detailed kinetics, the last data to provide during the setup is the distillation curve for the selected fuel. Ricardo provides multiple pre-computed distillation spreadsheets in the installation directory for various surrogates such as PRF, TRF, ETRF, and a few others for diesel fuel, such as the one that we will show here for the ETRF surrogate. In this spreadsheet, the user can fill the ethanol content, the aromatic content, as well as the research octane number of the surrogate. The liquid and vapor composition are then automatically calculated as a function of the evaporation progress variable. Additionally, the TRF mixture that will be diluted with ethanol to obtain the final ETRF mixture is presented, as well as the final ETRF surrogate, with the composition in terms of ethanol, toluene, isooctane, and N-heptane by volume, mass, and mole in the liquid. Additionally, the moted octane number, as well as the density and molar mass of the surrogate, are given. In this case, if we use fuel B composition, we have 19.7% of ethanol, 23.7% of aromatics, and an octane number of 98.2. This gives us the composition of the surrogate with the liquid and vapor distillation curves. We can also look further at this composition, liquid and gaseous, with the two graphs presented here. In the case of the liquid, we can see it here plotted for each component as a function of the evaporation progress variable. And it can be seen here that ethanol evaporates faster than all the other components, and that past about 60 to 70% of the evaporation progress, there is none left in the liquid. Then we have both isooctane and N-heptane that feature relatively similar volatility, that then disappear or evaporate very rapidly towards the end, and toluene is the major component remaining in the liquid. Similarly, if we look at the vapor composition, ethanol here represents initially more than 40% of the vapor, compared to about 20% by mass in the initial liquid. So lots of ethanol is initially present in the vapor, and past 70 to 80% of the evaporation progress, there's almost none left in the vapor. And again, towards the end, there is a large amount of toluene that can be found in the vapor. And so these two graphs clearly illustrate the importance of volatility and differential evaporation on the spray evaporation and the mixture composition in the cylinder. If we go now for the demonstration, let us look at the simulation setup. We have the chemical mechanism, the fuel definition, and the EGR conditions as input for the Chemkin converter solution, which then generates the various inputs necessary for a CPV or an R2DK calculation. Using the inputs for the CPV, we can then calculate and set up the CPV calculation, which then provides a cloud file that can be used for the R2DK computation alongside the various inputs from the Chemkin converter solution. The detailed kinetics can then be calibrated on a single operating point and then run over a range of operating points to look at the emission measurement over the engine operating map. Before starting the demonstration, it is important, I think, to go over the terminology in VECTIS of what is called a zone. So a zone is a part of the fluid domain which may become connected or disconnected to the rest of the simulation domain at a certain point in the simulation. Cells are individually assigned to a zone through a process that we call zone painting and that we will illustrate during the demonstration. Typically, in IC application, we have the intake, the exhaust, and the cylinder as 3 separate zones. Zones are very useful in various situations. The first of them being that you can enforce a no-flow condition between the two zones when they're disconnected. The interface acts as a wall. They can also be used through condition modifier to apply modification to a specified volume only. For example, if we want to initialize swirl in the cylinder, and another condition for velocity in the intake and exhaust. And finally, it can be used in post-processing, such that average, integrals, etc. can be specified over a given volume, so that we can know the mean pressure in the intake, and same for the species or the mass of pollutants. If we now look at the detailed kinetic simulation setup that we're going to demonstrate just after this slide, we will use a single fuel and single operating point. The boundary conditions are also shared between the CPV and R2DK simulations. The present demonstration will go through the mesh generation, surface, volume, and the painting using the R-Geometry plugin from the RDesk tool and the meshing tools vMesh and vPre. Then we will go through the setup from scratch using the VECTIS plugin. And finally, we will be looking at post-processing sample results, both using the RPost plugin for charts and 1D post-processing, and RViewer for 3D data. Let's get started with the demonstration. Let us start with the mesh generation using the R-Geometry plugin. We can import our geometry. Like so. We can then rename the body and save the session. We can then add a surface mesh and select the body to be meshed. The global mesh size is changed and reduced to 1 mm to obtain a quite fine grid, and the other parameters are left as default. We can then generate the surface mesh. The resulting mesh will be near isotropic with triangular cells and watertight, covering the whole body. It is used during the volume mesh generation to compute the intersection between the background grid and the surfaces, and so good quality mesh is needed for both static and moving surfaces. We can now save the session, and we can see the resulting grid, which is nice and isotropic. We can then add a volume mesh, for which the first step is to define the bounding box, which is a box that contains the whole geometry and defines the background mesh and background cell size. We're using a cut Cartesian meshing method and define the background mesh size using length of cells with 2 mm in X, Y, and Z direction, and we leave the global refinement depth as 2. Okay. To currently capture certain physical phenomena, it is desirable to have a finer mesh in certain areas, such as where fuel injection or combustion takes place, which is near the top of the cylinder. Given that refinements can increase the computational cost, they must be handled carefully. Let us add a first refinement at the top of the cylinder, where combustion and fuel injection take place. And leave the default parameter for deep and force. We can then add a second refinement for the near wall refinement of the flame face and the valve seats. This allows to capture accurately the flow around the valves and the heat transfer along the flame face. Let's increase deep parameter for this to 3. And finally, let's add a last refinement, a spherical, around the spark, such that we can capture accurately the onset of combustion. The radius is 10 millimeters. The deep value would be 3 to keep a nice fine surface mesh, and force increase to 2 to refine the volume grid. Okay, we can now generate the grid. In the bottom left here, we have the output of vMesh. That is the Ricardo tool for generating volume meshes. It is being called automatically by our geometry. And on a laptop of recent specification with an i7 core, it will take about 1.5 to 2 minutes to generate the grid of 1 million cells. This fast turnaround is beneficial to optimize the cell distribution and allows the user to repeatedly try various parameters of combination of refinement, coarsening, mesh line position to result with the best possible cell distribution. It is also possible to generate a polyhedral grid by changing the meshing mode to polyhedral instead of cut Cartesian, in which case the refinement will also be applied, but the resulting cells will be polyhedral and not cut Cartesian. So we can see that the mesh is almost finished generating. So the volume mesh has been generated with about 900,000 cells and 570,000 internal volume cells. vPre is then called automatically to reorder the grid, which enables the optimization of the computation runtime by reordering the cells in an optimized fashion. We can now save the session and leave our geometry. The last step of the mesh generation is the zone painting. For this, we're using the vPre utility, to which we specify that there will be 3 zones, which will be the cylinder, exhaust, and intake. The grid to be painted is GDI.grd, and the resulting grid will be GDI engine zones. vPre then reads the volume mesh and the triangle surfaces and loops over each cells to determine to which volume individual zone it will belong to. As you can see here, it is done fairly fast and only takes less than a minute. Once this is done, we can use the viewer to examine the resulting mesh. So this is the engine, and we can paint by zone, where we can see the intake, exhaust, and cylinders have been painted. We can also examine individual elements, for example, and see that the zones contain only these cells. Finally, we can take a slice through the domain and look at the mesh to see that we have our refinement at the top of the cylinder, fine cells around the flame face, and a spherical refinement around the spark body. The mesh is now ready, and we can move on to the setup. Let us close our viewer. The setup starts in a new VECTIS session, in which the first step is to load the grid. Once it is loaded, we can extract it, create a fluid domain, and assign our material domain to a fluid domain. Then we will assign each boundary patches to a different boundary condition. In this case, we will have two open boundary conditions, an inlet and an outlet, and a single wall boundary condition, since all the walls will be considered isothermal. We can then assign each patch to its respective boundary condition with inlet to inlet, outlet to outlet, and all the remaining ones to the walls. We can also check using the 3D viewer here that inlet, outlet, and walls have been correctly assigned. We can then extract the grid. On the canvas, 3 elements have been automatically created, which are the walls, the outlet, and the inlet. We can now save the session. We can now continue the setting with the time-based setting, where simulation is unsteady, 4-stroke, and the number of multi-cycle is 1. In the global post-processing setting, we can write the residual and the initial solution in the post file. For the restart setting, we leave the default, but we also add a trigger for timed restart, such that we can write restart file at various important times of the simulation, such as the start of combustion, exhaust valve opening, exhaust valve closing, intake valve opening, start of injection, and intake valve closing. We can move on to the solver solution settings, renaming it. We keep the default for the global solver setting, and we change the simulation duration parameters with a time step of 0.125 CAD, a start time at start of injection, 419, and the end time here will be at the peak pressure, so 30 CAD, and the engine RPM is 2000. We can now save the session. Then we can move on to the setting up of the fluid domain. In this case, we can use a very powerful tool in VECTIS GUI, which is the setting template. This allows the user to either use predefined templates shipped with Ricardo installation for ICE gasoline, ICE diesel, batteries application, etc. But it also allows the user to save a template and to reuse it. In this case, I'm going to demonstrate using a custom template for R2DK fluid and steady gasoline application, which I'm going to load and apply. And then all the various parameters specific to this type of application in terms of relaxation factors, specification for moving boundaries, equations being enabled or disabled, post-processing settings are automatically set up from this template. So this allows users to pass on to each other the best practices and to save the best practices. Once this is applied, we can move on to the motion definition, where the motion type is changed to general boundary motion, and the other parameters are kept as their default. We can then move on to the zone definition, where we can rename the zone, the first one being the cylinder, the second one being the intake, and the third one the exhaust. Then we have multiple interfaces which needs to be associated with zone event to decide when the zone will be connected or disconnected. This interface is here, corresponds to the intake valve. So we're going to create a zone event for intake valve. This second interface is also linked with the intake valve. So both of the others are linked with the exhaust valve. So we're creating a new event and naming it exhaust valve, which we can assign to the last interface as well. None of the settings needs to be changed elsewhere. We can move on to now the solver settings, in which no modifications are needed thanks to the use of the template. All the various settings, such as bad cell treatment or equation settings, such as solver, linear solver solution, or under relaxation, have already been set through the template. We can now save the session. From this point on, we need to define the material phase that we are using in this session. For direct kinetic simulation, we are using multi-component mixtures that require a material library defining the properties such as viscosity, CP, etc. of every species contained in the mixture. This can be extracted from the Chemkin mechanism through the Chemkin converter solution. The inputs for these solutions are the three files composing the chemical mechanism: the transport, thermal properties, and kinetics. We then need to convert and extract three databases, one for the calculation of the R2 decay reaction rate, one for the material library, and finally the Conterra database. We can then run this solution by clicking on the Running Man icon. Once this is done, we can go back to the multi-component mixture and load the library from the RMT folder. Once the library is loaded, we synchronize it with the session, and we can see that the 98 species of the mechanism have been included in the session and can be found in the tree. We can examine these species properties by using the material editor. For example, we can look at the viscosity of various species. We can also look at the molecular weight, the thermal conductivity, or the specific heat capacity. Moving back to the multi-component mixture, we can now define the reactant, which is the composition of the fuel, the oxidizer, and the EGR. For this, we're loading the Conterra mechanism and defining the fuel and oxidizer composition in terms of mass fraction. Oxidizer here is pure air, and so the composition is 0.233 mass fraction of oxygen and 0.767 of N2. And for the fuel, we have our toluene with a mass fraction for fuel A of 0.404, isooctane with a concentration of 0.491, and finally N-heptane with a mass fraction of 0.105. We can now calculate the composition of the EGR using the pressure value at the intake, the temperature at the intake, and the global equivalence ratio at the exhaust. And we can then calculate the composition. And we can say here that the EGR is composed of carbon dioxide, water, and nitrogen, as expected from the stoichiometric combustion of an hydrocarbon. Once this is done, we can move back to the initial condition, which is defined in terms of a cloud file. So we're using the cloud file option and adding a cloud file initial source. Now, the cloud file that needs to be set up here must be defined in terms of real species. However, the CPV cloud file that we have extracted during the CPV simulation is defined in terms of pseudo-species, fuel, oxidizer, residual species, etc. So the first step is to convert the CPV cloud file to real species using this solution. We use the multi-component mixture defined, and we load the cloud file. Define the name of the new cloud file with real species, and run the solution by clicking on the Running Man. Once this is done, we can go back to our initial condition cloud data source and load the cloud file thus generated. We can then autofill the column indices to automatically read from the cloud file which columns correspond to which variable. And moving back to the initial condition, we can also check that the various species have been correctly assigned to their columns. You can check it with the output at the bottom. Finally, we can just set up the concentration for the cells which wouldn't be covered by the cloud file, which won't be the case here, but this needs to be set up nonetheless. In terms of the reference condition, nothing changes, we just keep them as they are. We are now setting the post-processing setting. In this case, we need a trigger for the 3D post-processing, which we will create. And this trigger, we want to export time-based event at the same time as the restart. So we can just go to the restart, copy the timing, and just paste them here. But we also want to export the solution as a function of the frequency during the cycle. At the start of combustion, we want to export every CAD. Then once the onset of combustion has finished, we relax that to 5 CAD, every 5 CAD. And then keep relaxing it to 10 CAD once 25 CAD has been reached. And all the way 200 CAD at the end of combustion. Then from the start of injection, we want an output every 20 CAD all the way to 600 degrees, where we relax this to 50 CAD. Okay, so once this is done, we can go back to our post-processing setting and define the trigger for the residual report, which is the default event trigger created with the session. This is a trigger which by default outputs the solution every time step. For the post-processing variables, we leave them as selected by the template. So this is the best practice for this type of simulation. And then the last thing left to set up is the list of species we want to see in the 3D post file. By default, every species is selected, which is not very efficient. So we can start by selecting only the best practice species, which is the species containing the fuel, oxidizer, EGR, plus a few other species, to which we can add acetylene, which is a soot precursor, but also adding formaldehyde, as it's an important pollutant and a species we want to keep an eye on, similarly for CH4. We can also deactivate the atomic hydrogen, which is not very interesting here, and similarly for the atomic nitrogen. But we can enable the N2O, which is a NOx component that we want to look at, and definitely enable ammonia and NO2 as NOx component. We can also deactivate the atomic O. This concludes the setup of the post-processing, and we can now save the session. We can then move on to the model definition for combustion, spray, wall film, turbulence, etc. So first on, the combustion model with the R2DK combustion model. The chemical mechanism folder corresponds to the folder where the R2DK kinetic database was stored, so the Redkin folder. We can then move on to the reaction rate scaling, which is essentially a multiplier on chemistry and is the main calibration parameter for the R2DK combustion. We use a zonal method, and given that there is no reaction expected in the intake and exhaust during the main burn event, these two zones are essentially disconnected from the cylinder, we can set the reaction coefficient to 0. This has the effect of skipping the calculation of chemistry altogether, and thus accelerate the solution. In the cylinder, however, we are putting a profile such that the reaction coefficient can be set to 0 when no combustion is expected, and 1 when combustion is expected, which means between the start of combustion and the exhaust valve opening, like so. We can then enable the soot post-processing variable to be exported in the 3D post file, and enable the soot modeling using the 9-step model. We can then add the turbulence model to the solution with a K epsilon realizable using unified wall function. We can then add the body force model, which will be used by the wall film model to account for gravitational effects. We can now add the spray model. For the solution control, we leave the default as they are, as they represent the best practices and the best compromise between accuracy and stability. For the spray gas coupling, we need to change the bandwidth to adapt it to the mesh, and the recommended value is about 2 times the cell size in the region of interest, which in our case is 1 millimeter. So the bandwidth is changed to 2 millimeters. For the wall film model, there's a similar conclusion for the solution control. We keep the default. For the momentum solution, given that surface wettability and capillary pressure are now leading order terms in this particular problem, we leave them disabled. The energy solution is kept untouched. The evaporation model is updated to subcooled superheated with default coefficient. And the sharp edge separation is activated. Now we need to define the link between the various components of the liquid fuel and the various gaseous species. This is a multiple to one link. Multiple liquid substance can evaporate inside a single gaseous species, or it could be a one-to-one mapping. But first we need to create the liquid substance and then edit it. Fuel A is first a TRF mixture with an octane number of 97.1 and 35% aromatics. We using a multi-component substance and the species properties modeling for the differential evaporation effect. We have 3 components that are toluene, isooctane, and N-heptane, and for which individual properties are defined in the liquid files for the toluene, the isooctane, and the N-heptane. We can then define the vapor and liquid composition using the distillation spreadsheet previously defined. Let's start with the vapor. We open the tab, and by moving to the spreadsheet, we can copy the vapor composition table, including the evaporation progress, and paste it. We can also rename the component toluene, isooctane, and N-heptane. We can then do something similar for the liquid composition by defining using a table, and then editing the table, copying the spreadsheet, and pasting. This now concludes the setup of the liquid material, so we can go back to the wall film model and edit the linked gas species, where the mapping here, a one-to-one mapping between the liquid component and the gaseous species is defined. So let's start with N-heptane, then isooctane, and finally with toluene. This now concludes the setup of the wall film, so we can save the session. Now that all the models have been defined, we can move on to setting up the injectors. For this, we're adding an injector to the canvas using hot volatile multi-component parcel with an injection rate of 10 millions per second and circular holes. The total injected mass is 83.6484 milligram with an injection start time of 420 crank angle. The injection rate is defined with a rate of injection profile using a mass flow rate and injection velocity setup with a minimum velocity of 80 meters per second. The rate is defined using an ASCII file, like so, and we can inspect the rate of injection with the temporal evolution of both the flow rate and the injection velocity in the table here and displayed on the graph. Moving back to the injector, we can set up the injection temperature for the liquid with 333 Kelvin and the liquid substance, which is our fuel A. Similarly to the wall film, we have to define the mapping between the liquid substance component and gaseous species. So the liquid toluene evaporates into the gaseous toluene. The liquid isooctane evaporates into the gaseous isooctane, and the liquid N-heptane evaporates into the gaseous N-heptane. Once this is done, we can move on to the models, where the momentum transfer using Putnam drag model with different coefficient, the heat transfer using evaporated particles with the Spalding model, the mass transfer, similarly to the wall film, uses Spalding superheated model with different coefficients. Primary breakup uses size distribution per hole, while the secondary breakup is activated and uses the Wright-Stewart model with different coefficients. The droplet-droplet interaction model relies on the O'Rourke model with adaptive collision mesh, based on average Weber number and 50 parcels per box. And finally, the droplet turbulence interaction is activated. Once the models have been defined, we can move on to the holes definition. The injector in this engine has 6 holes. We could use the hole setup, as shown here, but it is easier and faster to switch to the per hole setup. In this type of setup, all the common properties shared by the different holes can be set for the hole number 1, which can then be cloned 6 times to generate the 6 holes. The spraying gun is here 10 degree, with a diameter of 0.216 meter, a radial distribution coefficient of 0.7, a discharge coefficient of 0.65. The particle size distribution is created and defined using a tabular profile from an ASCII file. We can then examine the profile, which shows that the mean diameter of the injected parcels will be about 11 micron. Going back to the injector, we can now clone the hole number 1 6 times and switch to the table view to set the position and direction of each of the holes. For this, we can use a pre-filled table and paste it. This ends the setup of the injector, and we can see on the canvas that the holes have been created and are represented in the graphical window, as shown here. We can now save the session. Adding a spark to the session is extremely easy, with using the energy deposition model, setting up the spark position in X, Y, and Z direction, with a start time of 4 CAD, a duration of 1 millisecond, an initial radius of 1.5 millimeter, and an energy of 0.1 joule. We can now move on to the boundary conditions. First, let's go through the solid boundary conditions, where the condition type is prescribed temperature and is specified per boundary. We can then edit the thermal condition per patches, where the crevice temperature condition will be 430.9 Kelvin, which is the same for the flame face, the injector, and the spark plug. The exhaust manifold is at 396.4 Kelvin, and it's the same thing for the exhaust port seat, while the intake manifold is at 360.3 Kelvin, and similarly for the intake port seat. Finally, the liner is at 468.7 Kelvin. We can then move on to the spray, impingement, and wall film conditions, where the boundary conditions for which interaction is expected with the spray, with the liquid phase, will be set up with wall film and splashing. This is the case for the crevice, the flame face, the injector, the liner, and the spark plug. The parameters for the wall film with splashing models are kept as default, and the intake and exhaust port conditions are left as bounds, as we do not expect to have any interaction with the spray. Let's move on then to the inlet boundary condition. In this case, the boundary condition is defined using a mass flow normal to the boundary set by a time-dependent profile. Similarly to the cloud file, the boundary conditions are provided in terms of CPV species and need to be converted to the R2DK real species basis. For this, we're using a new task, which is the RTZF boundary to real species solution. By selecting the multi-component mixture and defining the boundary condition input files, we can then convert them into the new real species basis. We can give the name of the converted files and then run the solution by clicking on the running man icon. Like so. We can then move back to the inlet, select the file, the converted file, and move on to the outlet, for which we will select a static pressure with a time-dependent profile and select the file corresponding to the outlet boundary condition, making sure that the flow is set up as an outflow. Now that the static boundary conditions have been defined, we can move on to the definition of the moving wall boundary condition, which is the piston and the valves. Let's start by adding a moving wall here for the piston, renaming it, and selecting the surface file for the piston. The motion is defined in terms of a fixed direction with a file, where the reference time is 360 CAD. The motion file is selected, and the direction vector is left at -1 along the z direction. We then define the sliding boundary as being the liner. For the condition of this moving boundary, we're using a prescribed temperature with a temperature of 555.8 Kelvin and a wall film with splashing modeling of the spray impingement and wall film. The default coefficients are used for this modeling. A similar procedure is followed for the other moving walls. Now moving to the intake valves, where the surface file is selected. The displacement is once again defined in terms of a file with a reference time at 360 degrees. The motion file is selected, and this time valve curve modifications are applied with a minimum valve lift of 0.2 mm and a minimum displacement of 0.1 mm. We can see the modification of the valve motion here. The direction vector is updated. Before moving on to the thermal conditions, in which a prescribed temperature is used with 400 Kelvin, and wall film with splashing modeling is activated with default coefficient. Finally, a similar operation is done for the exhaust valve, for which the surface file is selected, the displacement defined in terms of a file, with a reference time at 360 CAD, a motion file to which valve curve modifications are applied, as shown here, and where the direction vector is defined, and the condition data with 450 Kelvin and wall film modeling with default parameter. We can now save the session. Now that the boundary motion is fully defined, we can use this knowledge to go back to the valve events defined previously to specify at which time the various zones are connected or disconnected. For the exhaust valve event, the type is periodic with a period type of the cycle value, which is 720 CAD in this particular case. And instead of defining manually the start and end time, or the opening and closing time of the valves, we can use just the time from the boundary motion and select the appropriate boundary, in this case the exhaust valve. We can then find automatically calculated the opening time of the exhaust valve, which is 140.4 CAD in this case, and the closing time. A similar operation can be done for the intake valves, where this time the moving wall is the intake valve. Once this is done, we can just reorder the element on the canvas to bring everything and add a bit of readability. As such. Let's now move on to the last step of the simulation setup with the addition of sensor. This is probably the most important step, as the sensor will allow for the post-processing and detailed analysis of the solution. Let's start with the definition of the monitoring point sensor, which measure variables at a given location in space. The data are outputted at every time step using the appropriate trigger, and the position of the monitoring point sensor is given. The spark plug location is used in this case, and the velocity, pressure, and turbulence conditions are outputted. The second type of sensor is the wall condition sensor, which again will output the variables at every time step, and the variables are kept as default. All the boundary patches must then be selected for both static and moving boundaries. Next, we will add the sensors for the inflow and outflow. The solution is outputted every time step, and the two boundary patches are selected. The variables outputted are slightly adjusted, such that the mass fraction of all the species and the soot are outputted. This is needed to measure the emissions of the engine at the exhaust plane. This can also be used to feed a catalytic process model to obtain the tailpipe emissions. After setting up the point and surface sensor, let's add a volume sensor. The sensor will output at every time step and will be based on the zones. Similarly to the open condition sensors, the variables are slightly adjusted to keep temperature, pressure, turbulence properties, and the composition of the mixture in terms of selected species only and soot. Additionally, the swirl and tumble motions are measured through the angular velocity and momentum, and the heat release, cooling losses, and spray statistics are exported. The swirl variable are then labeled based on the center of gravity around X, Y, and Z axis. For the species to be outputted in this sensor, we want to keep the same as during the post-processing. So for that, we can just go to the list of species in the post-processing, select this list, copy it, and going back to the volume sensor, we can just paste it. Finally, given the importance of what happens in the spark plug vicinity on the initiation of combustion, we want to add a sensor for this region specifically. To this end, we will add another volume sensor, but this time defined on an arbitrary volume. This volume is defined by a triangle file, the spark sensor here, which consists in a sphere centered around the spark plug. We can add the variables, and contrary to the zonal volume sensor, we are mostly interested in the thermochemical state of the mixture. Thus, the species that we're getting for this sensor are similar to the previous sensor. We can copy this list and paste it here, like so. This brings us to the end of the engine setup and has taken us less than half an hour. The last step is to validate the solution, and we can see that there is no warning, and it is thus ready to run after generating the input file. This is done by selecting the solver solution and clicking on the running man icon, like so. Once the simulations for fuel A and fuel B have been completed, it is possible to use Ricardo post-processing tools to examine the solution. As outlined at the beginning of this workshop, we will start with RPost, which will allow the analysis of the results provided by the various sensors set up previously. Let us add the result file for fuel A and fuel B. From there, we can start to examine the mixture composition in the spark region using the spark sensor. We can start by plotting the mean mass fraction of every fuel component for fuel A with toluene, isooctane, and N-heptane. We can do something similar for fuel B with toluene, isooctane, N-heptane, to which we need to add the ethanol, like so. This first set of results already shows an interesting feature of the ethanol addition in fuel B. In the early stage of evaporation, in here, we can see that the ethanol mass fraction is larger than that of the other components, even though ethanol only represents 20% of the overall fuel mass. This is similar to what we have seen previously in the distillation spreadsheet. This clearly results from differential evaporation modeling, which is captured thanks to the coupling of a state-of-the-art multi-component spray framework with a detailed mixture composition based on real species. We can now move on to looking at the overall fuel content of the spark region. For this, we're using calculated curves to add together the mean mass fraction of the various fuel components. First for fuel A, and then for fuel B. Like so. These results indicate that at the spark timing, which occurs here, there is less fuel near the spark in the case of fuel B than in the case of fuel A. Knowing that in both cases the injection characteristics are identical in terms of mass flow, velocity, etc., this is clearly an effect from the multi-component evaporation simulation. We can also see that this difference builds up a long time. To analyze further the near spark region, we can plot another set of identical curves both for fuel component and for the overall fuel, but instead of looking at the fuel component spatial averages, we can look at the spatial standard deviation. Let us copy the curves previously defined to this new page and change the source data from mass fraction averages to mass fraction standard deviation. Once again, the effect of differential evaporations are clearly visible with the early evaporation of a large quantity of ethanol compared to the other components in the case of fuel B. Similarly, for fuel A, the standard deviation of isooctane is much larger than that of toluene, although both species can be found in near identical quantities in the liquid fuel. But the toluene in the distillation spreadsheet was found to evaporate much slower than the isooctane. For both fuel, a relatively large standard deviation can be found at early times when the mixture is strongly stratified near the spark plug. Finally, we can look at the overall inhomogeneity of the fuel concentration by assuming that the standard deviation of the fuel mass fraction is equal to the sum of the fuel component standard deviation. For fuel A, we select the component, sum them together, and similarly for fuel B, we select the component and add them together. like so. Here again, we can observe a very large standard deviation at early times stemming from the ongoing mixing. What is more interesting is what happens here just before combustion. The standard deviation of fuel B is about half that of fuel A, indicating a much better mixing in the near spark region. When remembering that mixture inhomogeneity promotes pollutant formation and is detrimental to flame propagation, one can expect fuel B to burn much cleaner than fuel A. Note that the entire analysis shown here for the overall fuel content and the overall fuel inhomogeneity could have been done over the whole cylinder by using the zonal averages here instead of the spark sensor. We can now move on to the analysis of the flow field in 3 dimensions using a new session of the RViewer plugin. Let us load the post file corresponding to the fuel A simulation at spark time. And then create a new canvas and load the simulation for fuel B to compare them side by side. We can create 3 slices going through the spark plug in X, Y, and Z direction. And similarly for fuel B in X, Y, and Z direction. Let us now look at the fuel distribution in the cylinder for these 2 cases. For this, we are plotting the total fuel mass fraction variable, which consists in the sum of the mass fraction of the various components. We can hide the main plot and look at the cylinder slices. We can then change the range between stoichiometry minus 20% and stoichiometry plus 20%. We can see that in the case of fuel A, the cylinder is divided in 2 regions, one very rich near the exhaust and one very lean near the intake, and the mixing line is positioned roughly at the spark plug. In the case of fuel B, the mixtures appears much more homogeneous. There are still pockets of very lean and very rich mixtures, but they appear much more limited, and in good agreement with what we found previously with our post, the mixture around the spark plug is much more homogeneous in this case than in the case of fuel A. The total fuel fraction represents the level of detail available when using pseudo-species instead of real species. All the fuel components evaporate in the same fuel species. Since we have access to the individual component concentration with a detailed kinetic simulation such as this one, let us look in more details at the composition of the fuel B mixture. We will be looking at the local deviation of the gaseous fuel composition compared to the liquid fuel. For this, let us use a user-defined variable that will evaluate this deviation. We'll start with ethanol, and we will start by normalizing the ethanol mass fraction by the total fuel fraction, and normalize this result by the ethanol fraction in the liquid fuel, which is 0.206. As such, we can then select our slices and plot this new variable and normalize it to a max deviation of plus or minus 15%. In this case, we can observe a region near the right of the cylinder that is on average deprived of ethanol, while another one on the left is on average richer in ethanol that would be normally obtained by neglecting the differential evaporation effect. A similar analysis can be done with the toluene component. For this, we can copy the ethanol user-defined variable and apply it to toluene by replacing the ethanol by the toluene and the fraction in the liquid component. This variable can then be plotted and the range be reset to plus or minus % deviation. Once again, a clear stratification can be found, where a very large pocket of toluene-rich fuel can be found in the same region where ethanol was found in lower quantities than in the liquid fuel. Since toluene, which represents aromatic hydrocarbons, tends to promote soot formation, the effect of this stratification on the powertrain pollutant emission clearly needs to be accounted for. This cannot be done using a lower fidelity modeling approach based on pseudo-species such as RTZF or CPV, but this is accessible with a detailed kinetic simulation accounting for differential evaporation effects. This now concludes the Ricardo software VECTIS suite demonstration for this workshop. In summary, detailed kinetics allow an accurate simulation of fuel composition effects such as differential evaporation on the cylinder mixing, combustion, and ultimately on the pollutant emissions. This stems from its ability to account for the numerous chemical formation pathways and incomplete combustion effects, themselves resulting from the fuel stratification and local composition changes arising from component volatility. However, this type of simulation is computationally very demanding and previously could not be easily integrated within a virtual product development process. In this workshop, we have illustrated a novel workflow building on the strength of the Ricardo software 3D toolchain VECTIS that allows for a fast and accurate simulation of the fuel composition effects on the power and emissions profile of a powertrain. By leveraging the use of a lower fidelity modeling framework, the CPV, to reduce the overall computational cost of the very accurate R2DK framework, it becomes feasible to integrate detailed kinetic simulation in a virtual product development process, where it can be used to inform the development of 1D models. It thus contributes to the overall improvement of engine digital twin simulation fidelity. These improved digital twins will contribute greatly towards large savings on both hardware testing and development time. Furthermore, the very sleek and integrated user interface of the Ricardo software suite makes the setup of such complex simulations very efficient, such that a setup from scratch does not take more than 30 minutes. It thereby frees precious engineering time that may be devoted to further analysis of the results.